What makes temporary works over water different? So there are a few points that I'd like to make here. So we're a key one is that we're working on either unstable ground due to the presence of water, such as on beaches or on riverbanks, alluvium. These areas are generally very poor and lead to difficult ground conditions. Or we could have no ground at all. We could be totally just on the water without any ground. Or another eventuality, we could have the same project that we have both some ground and no ground, tidal rivers or coastal tides. Then that can pose quite a significant constraint on a project. The loadings can be very different as well. Water loadings from waves or flowing water can be significant and not to be underestimated. Access is usually an issue, so this includes up and downstream structures such as bridges, getting plant and materials to site. If you're isolated between some low soffit bridges, that can be very difficult. And many historic waterways such as canals, they weren't built for the kind of plant that we find commonplace today, so access can be quite tricky. Land ownership as well, linked to access. So space is premium, and getting that space is quite difficult usually. Another one is poor weather, so that has quite a large impact on these types of works. If we're in a very large open space and a water course, then the wind can be significant. We can get much higher wind speed on those large open spaces, and then as a result of that, some large waves and swell, which can cause stability issues on if we've got floating plant or floating structures. In addition to that, because we've got that high wind, so for example, a large lattice crane jib, for instance, if that's going to be exposed high up in this kind of very exposed area, then that's going to draw a significant amount of wind loading, which is all kind of tracing back to the barge, which or platform that it's on, causing potential instability. Another one here is environmental risk, so containing any debris or contaminated material. That's quite a challenge. It's not something that you could drop onto a sanitary surface like concrete and then think, well, we'll just clean that up later. Water courses are complex ecosystems that are very sensitive to change, and if you drop something in there, it's not necessarily very easy to recover. Accidental impacts and dynamic load. So this is quite different as well for these kind of structures. Different plant creates different forces, and crawler crane lifting a steady load is generally predictable, for example. But if we've got an excavator doing some dredging work, if it's doing some rapid dredging or scooping and pulling things up and then dumping it off, then that's going to be exerting a much larger, more dynamic load on the barge. Waterborne impacts from floating debris. That's also important to consider. So that's something floating down, coming down river at pace sometimes, or impact from a vessel, which kind of takes us on to unexpected forces. So what if the excavator has to dig in unexpectedly stiff ground, or it pulls harder than planned? Then we need to anticipate those real world scenarios, which is where experience comes in. And we often have to apply an additional load factor on top of that, increasing load sometimes between 25 to 100% to account for these dynamic and operational unknowns. And then finally, I've added on the end there, supply of power, equipment, and disposal of material. Although not a real design requirement per se, it's just important that we have a solution that works to supply, and this our disposal is really key for these successful projects. So in summary, there are a number of significant challenges associated with temporary works over water. But those who enjoy a challenge, it can be incredibly fun. It takes you to some pretty awesome structures, and those unique challenges that these projects offer mean that we've got some different solutions that apply, and getting to that right solution and seeing success is what engineering is all about for me. But success can only be realized if we have the correct solution in the first place, and that's getting to this solution efficiently requires two things for me. two key things. So one is understanding the problem in the first place, and then two is good knowledge of those effective solutions and their benefits and limitations. And with that GIGO, or garbage in and garbage out, it's really important to understand the project constraints, the build-up or construction of the structure. For these kind of projects, having water data, such as the flood risk and flow rates of the river or water course that we're considering, things like that. That's really important, and these have a really large influence on what that final solution will look like. So the other part, and once we've got that understanding, the other part, which is part two, was to know what kind of solutions and have that experience of those typical solutions of what's available in your toolbox and what would be appropriate, the pros and the cons. So we're going to look at some of these typical solutions that are employed on projects when we are near or on the water, and they can be broadly split into two categories for me: near land temporary work solutions and then offshore temporary work solutions. So although some examples do kind of cover both, they can be on near land projects and offshore, I've kind of split them up into those as best I can. So here we've got a list. So we've got barges and pontoons. These are floating platforms of various applications. We're going to cover some of that today. Dams, so prevent or stopping water, over pumping rivers or short-term dewatering are often used on those. Soil berms in water, so extension of platforms or additional support to platforms. Jetties along and access along water courses. Temporary bridges, proprietary or scaffold bridges, depending on the application and the weight that they've got to support. Piling gates, so they are essentially guide frames for installation of piles through water. Buoyancy lifting, so that's something where you can use either the baffles and tanks in pontoons or barges where they're hollowed out essentially, and you can use that buoyancy to lift structures. There's other methods, so you can pick things up by jacking on top of barges, or use the barge itself, or the vessel and the pump chambers to use buoyancy to great effect and lift things up. It can be quite considerable. And finally, water storage. So you can actually link to dams, so you can use a proprietary damming system and store water somewhere where it wouldn't be able to store before. Some offshore applications. So we've got floating plant, so that's going to include jack-up barges and large jack-up barges, larger vessels, semi-submersible cranes and platforms, so the kind that you see lifting up whole oil rigs for transport, those huge vessels, using buoyancy to pick those up. That's quite impressive structures. Also offshore foundations such as monopile installation or jacket construction, as well as how structures and plant materials are transported across seas. So the stability of these is very important if you want to ensure that you don't find that your very expensive piece of plant is at the bottom of the ocean. So just some examples there. We're going to take a deep dive into a couple of these examples today, the first of which are going to be temporary dams. So a temporary dam in construction is a watertight or pretty much watertight enclosure built within or across a body of water, and that's to isolate that work area and allow that work area to be pumped dry or dewatered. Those pumps usually continue to operate and work, so the dam doesn't have to be very, very watertight. It's just to mean that you can carry on your pumps and it's still a workable solution. The key loadings are water retention, and they are often used for building or demolishing or repairing bridge piers and foundations, or permanent dams. So often we'd have an upstream and a downstream dam, and then that would dewater the area to allow that work to happen. And then retaining walls as well, so things like flood defences, riverside walls and canal walls and things like that. Some common types of dam are listed here. So firstly, we've got a water-filled dam. This is like a large kind of sausage-shaped structure, which is filled with water and has an impermeable membrane around it, and basically just holds the water at one side and retains that water. It's quite an effective solution, and it means that you can install it in most places because it's very versatile, and because of its structural type, it's very good at filling all the little gaps and odd profiles that you have. So you can see the couple of examples there. We've also used this as a deck support for a very low profile bridge over a small watercourse, because it was able to be put through underneath the bridge where the watercourse was, and then filled with water. It stabilized the abutments and also provided as a support to a deck. So they're quite a useful system and different applications. Here we've got a porterdam. That is a steel frame structure that has a impermeable membrane liner on the face of it, and it is used to hold back water. So it's really the hydrostatic pressures that you get from water that it's resisting. In a frame, it needs some fairly decent foundations and is limited in its height. You can raise it up and put it on some kind of rock-filled bags, for example. But they're a really useful solution in terms of holding back water in a particular area. So it can be just an area inside a canal or a river, or it can go across the whole kind of area like shown on that photo. That's a pretty handy solution, a porterdam. The next one here is a gravity mass-filled dam. So you can use legato blocks or bulk bags full of ballast, sandbags as well. It's essentially using a similar application of the water-filled dam, but it's just filled with 6F2 or something like that. So you put a impermeable membrane around it, and therefore it holds back that water. There's a few applications. It's good for the smaller water courses as well. Here's one that we've done down Cornwall Way. It's partly constructed there, and you can see that the bulk bags are full of material, and that was installed to enable some repellers to the quay wall down there. So that's a very handy solution. It's also quite versatile because you can use sandbags and to fill small gaps as you build the dam. So it's quite handy. The last one here is a cofferdam. So a cofferdam is a temporary watertight structure. It's usually constructed from sheet piles like shown here, and they are there to hold back those water loadings. It's very similar to like a sheet and whaler excavation support system, but they're built just to hold back the water loadings and to enable some form of construction work or repairs to take place. And then once that has been completed, then they're removed. They're very similar to a caisson. So a caisson is basically the same structure, but that is typically a permanent structure. So a caisson is that permanent watertight structure that then becomes part of the final building, and you often see them in large foundations that are cast for new bridges, where a caisson is installed, and then the foundations basically fill those caissons. Let's look at some applications here. So we've got overpumping. This is where we've got a dam upstream and a dam downstream, and then we have installed something like a porterdam. You can see there's some remnants of a porterdam, which I've taken a photo of there, the impermeable liner on the floor in white, and then the framework of that porterdam. So that's installed upstream and downstream, and then there's some pumps installed where you can see on the top right of the screen, and that basically pumps the water from upstream down to downstream, so we can bypass the area that we need to keep dry. The specification of the pumps is really important so that we don't get the dams failing or overflowing, and then water entering the area is supposed to be dry. That's a pretty typical application. Another one here is an example of a river wall or canal wall that needs to be demolished and rebuilt. So we've got some sequence drawings here. So the first stage here, we've got a working platform going in, and some of the new wall coming in and installed there. Then the next stage is that we've got the porterdam system. On this particular project, we use the porterdam system. And you can see that's shown in orange, and that's holding back the water. And that was kind of in a localized area, so the water was still able to, or the water in the canal was still able to flow around it. But it meant that we had a dry area to carry out the operations. Next step here is that wall is demolished and a new wall is installed. And you can see that there's the installation method of that porterdam system. So the framework is installed, and we place the membrane, and then we can dewater that. And then the subsequent stage to this is then to, once that new wall is in and complete, then the porterdam can be removed and the works are complete. Okay, so that's a little bit on dams, a bit of a deep dive on dams. Next, we're going to look at some barges and pontoons. So we're going to look at reviewing those. And to define what a pontoon or a barge is, we're going to run through some key aspects of what they are. So first of all, it's a floating structure. It needs to be buoyant and it needs to be stable underwater. They're typically flat bottomed, and that provides that stability and makes it easier to connect multiple pontoons together. That leads us to the third aspect, is that the pontoons are typically modular, and you can connect them together to make different shapes to suit whatever arrangement you require for the plant or equipment that you've got on there. They can sometimes have spud legs, which are the two columns that you can see on that photo, and they are deployed to provide additional stability. They can be in various locations, in 4 locations or a couple, to suit what is required and necessary. It's important, though, to understand that if stability of a particular activity or system wholly relies on those spud legs, then and they are the primary source of stability, that it's important that we understand very clearly that fluctuating levels can lift the pontoon up, and then it would mean that the legs are not deployed, which could lead to instability. So it's just a note there. They're usually made from pretty strong materials, depending on the application. So for heavy works, then there would typically be steel. But then for lighter weight works, then they can be typically made out of a high density polyethylene, a high density plastic. That's the kind of system that you would typically see for leisure craft and pontoons, where people are using leisure craft or along leisure marinas and things like that. But they can also be used in construction. And then finally, a great advantage is, and why they're so often used in temporary works, is it provides quite an affordable and temporary solution, as opposed to having to build a proper structure. Barges are very similar, but they often are just a rectangular platform, look a bit like a canal boat. Sometimes they're just an empty tank, so they can be used to for storage of materials if you're dredging a canal or something like that, and then the material is placed into a barge. Or they often have plant permanently mounted on it, so an excavator with just its instead of having tracks, it's just mounted on top of its slew ring. Barges and pontoons, they're typical definition. So they can be very useful for working platforms and access platforms. They can be joined together, creating those stable platforms, and provide access to operatives over water or plant. So it can be very commonly used for bridge construction and maintenance, or pipeline construction and maintenance, diversion works, or marine construction or maintenance works. So you can see in the bottom right hand corner there, that's a more of a system, a lighter weight system. They're like the plastic pontoon types, and they all link together in their modules. So that's the kind of thing that has been taken from the kind of leisure pontoon and used in the built environment, whereas the other examples there are probably a bit more heavy duty, heavy application, requiring some heavy materials. Here's a few examples of dredging operations. Dredging is the excavation of material from water, essentially. In the UK, it's generally used to remove the accumulation of silts or fine gravels that have been washed into rivers or canals from surrounding land, and it's carried out just to increase that river flow and as a flooding control measure to make sure they're getting all silted up. So the excavator will be sat on one of the pontoons or a barge, removing material and placing it into a barge for that material disposal. In the centre, we've got a piling operation sat on a pontoon. And the application is similar here. We've got a plant operating on that pontoon and installing the piles as shown. And then finally on the right there, we've got pontoons used as temporary bridge supports, supporting a proprietary bridge across a watercourse. Quite an effective temporary solution. Also quite lively foundations, but suitable for that application nevertheless. Okay, next we're going to look at how we calculate stability on these structures, it comes from the naval architecture of vessel stability. So we're going to deep dive into some of the critical part of that temporary works engineering, and that is how we ensure that the plant that is floating, how it maintains stability. It could be carrying cranes or excavators or equipment, ballast, all sorts of stuff that we put on these pontoons and barges, and it's essentially about making that floating working platform remaining upright to the point where it's practical to carry out operations on there and to maintain safety. So in simple terms, it comes down to the battle between two key points, really. So it's the center of gravity, which is noted as G there. This is the combined average center of the weight of the whole system. So it's the crane, the load, and everything on board, and we want this to be low. Generally, we want that center of gravity to be as low as we can. And then we've got also the second part is the metacenter, and that's noted as M at the top there, and the distance from the base to M, km. This is a theoretical point that represents that floating platform's inherent ability to resist tipping. And so if that is very high, then that means that we've got a fair bit of stability here. And the difference between these 2 points are called the metacentric height. That's what tells us if our platform is stable. So for stability, that metacenter must be higher than the center of gravity. If the center of gravity is essentially too high, then the craft is going to be very unstable and could rotate until it capsizes. Essentially, so that's what we're looking at doing. And so how do we do this as engineers? We calculate those 2 key points. And for the gravity, G, we precisely calculate the weight and the center of the gravity for every component on there that we're expecting on there. So it's the pontoon itself, the jib of the crane, anything that with any equipment on there. And then we've got KB, which is K2B, which is the center of buoyancy. And we figure that out where the upward push of the water is acting essentially. And this is based on the volume of water that the barge or the pontoon displaces. That's where that buoyancy load comes from. And then we've got B to M, and that is the distance between that center of buoyancy to the metacenter based on the various barge or pontoon dimensions. So we can use a simple equation, which is that Km equals Kb plus Bm. And then we can confirm that the total height of that metacenter is safely above the center of gravity, which means we've got stability. To increase stability, we could do a number of things. We can make the pontoon wider, which increases that B to M factor, or we can reduce the load. We can introduce ballast and kentlage essentially to counterbalance any loads that we've got a load which is really pulling the eccentricity to one side. We can ballast it up on the other side. It means that the system is going to sit slightly lower in the water, but it means that we've got some stability. We could also utilize compartments or baffles which are within the barge or within the pontoon, where we can pump water into these and they act as additional ballast as well. And what that does is it draws down the center of gravity to much lower, so that provides an effective way to trim up and provide stability. If we provide something like an eccentric load to the pontoon or to the barge, then that tries to destabilize the barge and leads to instability. And the check is to make sure that we've got enough stability that we can have a destabilizing load which is realistic and we expect, but it still doesn't capsize the barge, and we have enough stability in that system. But even if the stability check is perfect, we have to review what happens actually during the work. So for plant location, placing heavy plant far on one side will cause it to roll. And that reduces what we call the freeboard, and that's the distance between the deck and the water. So if the freeboard, for that example, on the left there, the freeboard is quite close to the is low, so it's quite close to that water. If we've got a low freeboard like that, and we've also got waves and swell, then that's going to enter onto the top of the pontoon. We generally need to keep that roll low down, generally below 7 degrees or something like that for safe working. Slewing effects as well. So if we've got particular plant dredging or craneage as it's slewing around with weight, that can cause some instability and shift the central gravity as well, and causing that greater roll effect. We need to make sure that the plant that we've got working on top of these systems are working safely, and we aren't causing too much of a slew effect on our structures. Once we're totally happy with all of that from a stability perspective, of course, on top of that, we need to make sure that the system is actually structurally adequate. That if it's a pontoon with multiple modules, that the connection between those is suitable. The modules themselves can deal with the loading from perhaps point loadings from craneage or excavator tracks, that we're carrying out those proper structural effects. Obviously, it can become quite complex. That analysis can be very complex if we've got significant amount of material or operations or plant acting on top of that pontoon or barge. The simple exercises are just a piece of plant on top of it, but more often than not, we're looking at some quite complex activities. One such complex operation was during this case study, which I'd like to share with you today. And this is Ottley Footbridge redevelopment scheme, which we're going to review with a specific focus on the use of pontoons during demolition. The principal contractor was Balfour Beatty. The demolition contractor was S. Evans and Sons. We acted as the demolition engineer, also calculating the stability of the pontoons, and the crane and the jacking was carried out by Sarans. We've got a photo here on the right. I've put a box around the bridge that we are looking at. This was a footbridge which had passed its design life and required replacement, but this is quite a strategic crossing point in Ottley, and so it wasn't something that could just be removed and replaced without providing some alternative. So you can see at the bottom of the photo there was a temporary bridge which was designed by Balfour Beatty and installed. That enabled the pedestrians to cross the river, and so we could close that footbridge. Access was very, very difficult for this bridge. So on the right hand side, there was limited availability to site a crane. We could only just get a small crane there. And on the left hand side, we also had limited of availability of the crane that we could use. So what was a key driver to this was that crane size could only be so big that we couldn't pick the beams up all across the river. That led to a solution where we needed to support the bridge, individual bridge sections that linked between the abutments. We needed to pick them up, float them out into the river to a location where the crane could then pick the bridge section up and then take it away for processing. The scope of the works is shown here, so you can see that it was across the whole elevation of the bridge. And if we take a look at that section, then the scope was to remove an addition to the historic bridge. It was a cantilevering reinforced concrete footway, which is cantilevering there, and you can show that you can see that I've shown in red the area that is going to be removed. These were precast eye sections, concrete eye sections, and they were going to be removed. One of the key constraints as part of this was inside that footbridge, there were some services. They were they were within the bridge and they had very little slack. So they had to be suspended from a system that was designed by Balfour Beatty before we could carry out the removal of those spans. Because we had the services there and we had the support system in place as well, which you can see. I'll show you on a later stage. But because they were suspended from above, that meant that the decks had to come out from underneath. We utilized a jacking system, which was sat on top of the barges, on top of the pontoons. And the pontoon was designed to be moved around by the tugboats in the watercourse. And so we could move the pontoon beneath a particular area and remove that part of the bridge and then work our way onto the next span. So you can see in this stage here, we've got removal of part of the deck and the handrails, etc., and installing the jacking system underneath, which would then enable us to take the first span here, carrying out stick cuts on those beams, lowering the system down so it was clear of the services, and then taking it away on the pontoon. That was the idea. You can see once that was carried out on one span, then it was repeated on the other spans. And then once we got to the end spans, these were close enough to the cranes where they could be removed just with the crane. So we would lower them down onto the pontoon, bring the pontoon out, and then pick them up again with the crane for further processing. A couple of images of the pontoon itself in action. So you can see that here it was being built. We've got the jacking towers, which were provided by Sarans. There's a number of different equipment on there, which all had to be understood and included in the assessment of the pontoon. And it was essentially towed out into the watercourse to be used to remove the bridge bit by bit. We used like a high density plastic docking system as the pontoon segments. You can see that there's many segments to make up that pontoon there. They were all connected together to form that main pontoon where the jacks were sat on some steel mats and then on some timber mats to distribute that load and to try and mobilize as much of the pontoon as we could. A photo here of the crane operations in use and an image of that worst expected heel, which is the angle of rotation or roll of the pontoon. Looking at the worst case scenario, if we've got wind and an accidental impact and a slight eccentric load from our system, if we were to miscalculate where the cuts are going to be, for example, we wanted to make sure that if we were to get some form of heel, which was calculated, that we wouldn't bottom out the pontoon onto the riverbed, because then it wouldn't be able to be moved along. And that was really important to be able to lower the beams down to pull the pontoon out into the watercourse and then pick the structure up with the crane. And that was one of the key challenges associated with this scheme, was that riverbed profile and the rock armor that was around the abutments. It meant that the depth between the bottom of the pontoon and the riverbed was very shallow, and that meant that the operations were quite restricted. And we included ballast, so ballast are around the pontoon so we could mobilize more weight in different locations of the pontoon to try and stabilize it as a contingency plan. Other key challenges so we've got access limitations. As I've mentioned, it was very tight and the road remained open during the works. We had the water levels which were very shallow. Riverbed profile was key to ensuring that the pontoon, as we expected to work, would work. The services in the bridge, they were very tight and they couldn't be moved. So they were suspended pretty much where they were, which meant that we couldn't just lift the sections out. We had to lower them down and then lift them out. The primary beams that those decks sat on were being retained, they couldn't be damaged, and then the cutting operations, which were carried out by core cut They were going to, if they were carried out either side of that span, and we needed to make sure that any debris or slurry that was going to be coming out of those cutting operations as we cut those beams would be captured and wouldn't enter the watercourse. So we included that into a couple of pontoons, smaller pontoons, either side of the main pontoon, and some visqueen as a working material to keep that slurry from going into the watercourse. So a number of key challenges there associated with that pontoon works, but yeah, that's the structure as pretty much most of the deck removed, and yeah, successful job. I'm going to hand over to Dave now, who's going to take us on to a case study more along the realms of the kind of environments that these structures can be in, or temporary structures and permanent structures can be in when they're in and around water, and the degradation of those. So over to you, Dave.
Yeah, thanks. So yeah, I struggled to come up with a nice case study for working over water that I've not done recently and boring you all with it. So I've decided to talk a bit about the structures that support a lot of the works when we're working around water. So kind of jetties, dock walls, and that kind of thing. And I'm just going to touch on what causes them to be quite a challenge in the marine environment, which I'm sure you're going to work out is seawater. So firstly, I'm going to chat a bit about kind of old masonry walls, fairly common around the UK on a lot of docks and things. Generally, if you assess these to a modern code of practice, it can be challenging them to make them work with the information that we have, though obviously they've been stable for a significant amount of time. So this was one I did a number of years back over on the west coast of Scotland, where we were challenged on if we could put loading behind this fairly sizable dock wall. I think it was 11 or 12 meters high down to the base of the dock, and it'd been there well over 100 years at this point. So with this one, luckily we had a fairly good archive drawing, as you can see to the right there, that noted that there were some counterforts, though we didn't know where they were. It gave us the fill kind of around the fill that had been put in behind the dock walls, and we knew all the water levels and things. So we could make the assessment, and we could actually prove this was suitable for the loading that we were going to be putting behind it. So as you can see there's a nice little kind of sketch of how we assessed this, kind of conservative ground parameters we took. And some of the interesting things that we found on this one, there was a number of large bollards on the wall. And if you looked at historical standards for what these would probably be subject to load-wise, they were fairly significant. So the old kind of Reynolds book from the 40s gives you some idea of about 15 tons acting in a variety of directions, and even modern codes of practice are fairly similar for docks of that size. So if we're dealing with structures like this, look for the strong points where the bollards are, because they will be designed for some fairly significant lateral loads, and it gives you some confidence that the kind of whatever pressures you're putting onto your wall are kind of going to be within the design loadings. When it comes to inspecting these and making sure they are in reasonable condition, generally you're looking for like bulges in the wall or any deflection or lack of verticality. Normally they're built at a bit of a camber backwards anyway, but any areas where it is tipping forwards would be a big sign of there are some problems with this wall and you probably don't want to be loading behind it. And that can be all done non-intrusively. You could then do some trial holes down the back of the wall to identify fill and how the wall was constructed, and you could potentially locate any counterforts if they exist. So moving on, the next one I'm going to talk about is kind of steel structures in the marine environment. So here's an example of like an under jetty assessment that we carried out. We were looking at the condition of the jetty above, and you can see there the concrete was a bit spooled, but not significantly given the actual thickness of the deck there. The more concerning element on this jetty was actually the corrosion of the steel in the low water zone. So there's some examples there of the condition of some of the UC pile sections that have been driven in, and where there was significant loss of section, you could say, right at the low water point. There was also a number of ties on the sheet pile wall, and a lot of these snapped over the years. So there was some issues with this structure. Luckily, it was being demolished as part of the work, so it wasn't a problem overall. We just had to justify the temporary condition and the loading we were looking to put onto it. So why is this happening? So there's a couple of reasons. If Josh clicks onto the next slide, so you do get a lot of corrosion in seawater for obvious reasons. Eurocode 3 gives you an idea of the kind of level of corrosion you would kind of design modern things for, but it also has a very kind of useful note that goes with that, which talks about the kind of accelerated low water corrosion, which is not covered in this and is due to kind of bacterial reactions at the low water zone. And it notes that it is a kind of a very random attack and can result in very significant corrosions quite quickly. So what I want to get at here is that it's important to inspect these structures at low tide, make sure that the steelwork that you're going to be relying on to support what you're loading is in a reasonable condition or still there, and to kind of just ensure that what you're doing is going to be safe. So that's kind of steelwork in general. You're kind of worried about that corrosion right at the low tide mark. So it's quite hard to tell if you're not doing that inspection at low tide. So moving on to concrete. So here's some images of it was a precast concrete structure. This one is well above the waterline, but there are some signs of cracking. So what you should be worried about with concrete in the kind of seawater or due to kind of a lot of road salts as well on bridges is the kind of the chloride content. So I'd say a really good reference for this, there's a BRE Digest 444, which gives a lot of good information on how this process works. It'll be far more informed than I will ever communicate via this presentation, and it's a good kind of background reading. But in general, prior to the 70s, sometimes chlorides were added to concrete as an accelerator to improve curing. And even after that, the chlorides in seawater and de-icing salts increase the chloride content of the concrete over time and will cause corrosion. It's the simple summary of it. So how that is generally shown when you're inspecting it is you will get cracks in the concrete and you will get kind of rust staining or kind of white staining of the concrete. And you will then start to get spalling as the concrete as the reinforcement corrodes. It kind of expands and kind of flakes off, and that will cause the concrete to spool, and you'll have some obvious signs that there is an issue with your structure. And as well as that, you will get deflection. If you're loading it towards its extreme and you've kind of lost reinforcement area, you'll get a more significant deflection. So they're the things to look out for. There's other issues with concrete in seawater, but chloride attack is probably the main one you should be worried about. And yeah, I think that's a summary of the kind of the three things I want to talk about with regard to marine structures and their assessment. But it's just very important to inspect these before you get involved and start loading them.
Thanks, Dave. And so as a summary slide, really, we take some of these key takeaways from today in temporary works over water. So first of all, understanding the problem is really important, and that process can take a little bit of time. Think of that GIGO that we covered at the beginning of today, and also understanding what the structure is that is supporting you, which Dave has covered. Another one is that not to underestimate the forces associated with water, as failure can be catastrophic. As you've seen, dam failures and of all kind of scale can be catastrophic once the water starts to get a grip of and surpass the capacity of the system, which is supposed to be retaining it. A small failure can lead to a progressive failure of that dam system and then a catastrophic collapse of that system. Works that are near water are often very constrained and very complex, so it's not to be underestimated. And then finally, as well, as a note about how aggressive the environment is adjacent to water, especially in the marine environment. on structures and can lead to some high corrosion or cracking of concrete from chloride attack. There's lots of information out there. There is Dave's mentioned some BRE content. There's content on the Temporary Works forum. There is ICE publications. There's a couple there that are really good kind of background reading and overall summaries. That's the Temporary Works principles part 1 and part 2. And then our YouTube channel as well. That's not just on Temporary Works of water, but for just Temporary Works full stop. There's tons of content on there covering demolition, construction, all sorts of stuff. So if you would like to know more about the subject, then those are some pretty good resources.